So hello, this is interesting. So obviously I'm tearing this further apart. And after a whole lot of sticker work, you can start to see that there's actually space for another rotary encoder, another button. You know, here's all the control panel LEDs and stuff like that. There's the button membrane. Take that out and just put that aside. The other button membranes, well, this one stayed. So what I'm doing this is because I can't figure out where the there has to be some non-volatile memory in here somewhere, because how else are they storing the you know, a lot of the characteristics for the, you know, like your codes and crap. But I can't see any non-volatile memory on the back side of the board. So what I am doing is actually, I think I didn't. Yeah, I do. So I am going to try and take the board out, I think. So back here we can see some interesting stuff. It looks like they've got this is kind of cool. So they've got, for each of the front end probes, it looks like they provide 2 rails, and there's fuses on all of them, which is very nice of them actually. You can also see we have D4, D5. Anyways, the reason I did all this is because I need to be able to, and you can see they've scuffed the front panel a little bit with whatever mechanism they use to tighten these nuts. So this board is a double-sided load. I can tell that from, you know, looking into the back side of it. So I mean, the main board is what I'm referring to. So it looks like the signal from any of the front end probes comes out of this cable and the power comes in here. And this power cable runs all the way over here and goes over there, whereas this cable folds around the other side. That's also kind of interesting. You can see they use flat-headed screws for some of these holes. So anyways, what I'm trying to say is that, so first of all, this seems to be the interface for the front panel buttons. And it joins into this board over here. So here's the interface cable, and it joins into this board, which then, just with looks like it just solders right to the board. And then there's another cable that runs under the LCD, and then comes up and joins this board. And this board's connected to that board. So it looks like all of the front panel buttons are kind of one coherent assembly. Here's the little seek thing. All little encoders, and then there's a cable that runs up here, and these are all glued down. DS4000 main key. DS4000 right key, and then left key. So, what I just did should have freed up this board, so now if I take out all of these screws, this board should come out and I should be able to take a look at the other side. So, I'm fairly confident that all these screws are the same length, because I looked at some of them earlier. I have to be very careful. Put them there. So I spent a little time, you know, going through all the component part numbers for this, and I can't find any non-volatile memory. So it could be like in the EEPROM for this device. But you know, basically the Blackfin has no non-volatile memory. These are all FPGAs, and they don't seem to. I don't believe they have any non-volatile memory. Weird ass FPGA. Look through a lot of the parts. You know, this device here is the Ethernet interface, it turns out. So I've been playing around with seeing if I could kind of hack the bus decoders. I actually took the chance, pulled the RTC battery back up, didn't do anything, interestingly enough. So whatever, you know, the RTC is apparently not involved in the bus decoders. You know, I've been corresponding with a chap on YouTube whose scope apparently, like, he was fidgeting with power, you know, resetting it multiple times, and suddenly it decided it was a DS4054 rather than a 4014. There's some question of whether or not this has switchable input filters, which is kind of what I'm hoping to evaluate a little bit. But I'm betting there's probably just like a little tiny, you know, I2C EEPROM somewhere, unless they're using some of the non-volatile memory in the in one of the ICs, like a microprocessor with non-volatile memory in it. But I haven't seen. I mean, this could be a microprocessor, but I didn't have much luck looking it up. But I don't see any other micros really, and I really strongly doubt they're rewriting the contents of the flash, because they'd have to, you know, it looks like, I'm not too sure how it actually stores. It's not date based because, again, removing the RTC battery back didn't affect it. So it's not like there's just a date stored somewhere in the non-volatile memory and then it just looks at the delta, because that would have been affected by my removal of the battery back for that. Lots of screws. They're all nice. They all have little shake-proof washers on them and everything. It's very nicely built. The only thing that I'm really mildly irritated by is the fact that there are screws under the sticker covering the front panel. I really wish they hadn't done that. Oh, bother. So, okay, that's annoying. So the display cable is obnoxiously located. I will show you. 1 second. Let me just put 2 screws in so I can flip this over without the board falling out. So it appears this thing has one very, very distinct kind of build-up procedure, and any sort of, you know, something else will just not work at all. So here are these 2 boards. I'm just loosening them. You can see that it appears that the cables running to these have basically just been hotbar soldered. That's interesting. It's got 3 standouts, but only. So one thing I note here is actually that there is there's a piece of polycarbonate or some sort of. No wait, that's actually glass. So it looks like they've actually bonded a. There's a sheet of glass held down with like some compliant adhesive tape on the surface of the LCD so that this is more wear resistant. That's an extremely nice touch. You know, in other words, this isn't just the bare surface of the LCD. There's actually a theoretically replaceable cover plate on it. So to replace it would take a lot of effort. You know, it doesn't look like it's been anti-reflection coated, but what have you. So you can see down here, we have a kind of an amusing little board-to-board jumper, or a jumper board. Flip that tab up. There's the LCD. So here you can see how there's this basically piece of sheet glass bonded on top of it with some adhesive tape. Let's put that aside. So, and then here's the connector I was having trouble with. You can see that it's kind of set down in there. I'm actually going to flip up this connector and then just pull the cable out. Anyways. There's 2 screws. So now, Shazam. So, here's the back side of the main control board. You can see there's not a lot here, though there is more SRAM. I would imagine that's more of the display RAM. You can see there's a can on the bottom side of the board as well. Let me get the case out of the way. So here's the bottom side of, we'll just sit fine on the heat sinks, that'll be trouble. You can see here's the BNC input section. And over here we have another 1117. Down here is a 25 megahertz clock, and I'd put money on it that's the Ethernet clock, because that Ethernet PHY is well, the PHY is actually up here, but you can also start to see that there's definitely some internal layers in this board. I wonder, this can looks like it's just held on with spring clips. So here's the bottom side of the analog input section. You can see they're all the same. Of interest is you've got a little Cosmo. I think I saw this in one other place. Cosmo little solid state relay, BNC inputs, boatloads of passives, couple unpopulated portions. What is that I see? That is a let's see, I can't quite make it out. HAS 595. Is that a 595 shift register? Huh. Anyways, there's some other interesting stuff, like over here in the trigger input section, we've got a bunch of little TO92 devices, lots of bypassing. There's the additional SRAM when there's some BGA breakout patterns. So what I'm kind of curious about, however, is what is that device? Where am I? I'm right here. Whoops. Two SAJP something 717. So that is a something 11208 325. Doesn't have anything that sounds like it would be a description for a. Where are my Q-tips? So there's only a few candidate devices down here which even could be EEPROMs. Got a little wet. Oops, I'm kind of blowing there. So, I mean, that's not an attempt to make it unreadable, it's just flux. It looks like this board might have been manually reworked. I mean, look at some of those caps. Looks like 111208, RC16 something 111208. We have some other devices. Is that an LP2990? LP2998, that's a power supply of some sort. In fact, that may be a flying capacitor voltage inverter, but I'm just kind of guessing. One more part over here. There's another LP2998. So right under the chip that is generally, you know, in the other teardown, people generally kind of came up with the conclusion that it was a PLL clock distribution IC. We have whatever that is, a JM23AC 387880J. So that's right under the PLL clock generation. What we think is, here we have some interesting differential pair length equalization. You know, these are two of the presumably the ADC ASICs. There are the other two. That there is another 2998, and that's about it. There's not much on the bottom side. There's some really, look at some of these chunky ass capacitor networks. So I'm not entirely certain where it's keeping its non-volatile memory, because I don't see anything that looks like it would be particularly relevant to that on this side of the board. Let me switch lenses again. The thing that's kind of interesting is you can see that for the cal output, the active lead is here and the passive lead is just a bent part of the faceplate. Anyways, so here's the actual front panel connector, and then this just has two junctions on the back that then run all the way across to the other side of the board over to here. And then presumably there is, I may pop that off in a minute, but let me seat that down on there. Then I have to kind of finagle the ribbon cable for the display through this slot just by being gentle with a pair of tweezers. I'll use my finger. There we are. So now I'm just kind of going to rip it by the BNCs up and over. I'm curious as to why they have two different kind of ground patterns. Maybe, I think this one is like a chassis ground strapping and these are just metal plated just so that they have good contact. Whereas it doesn't actually strap to any of the layers, because you can see there's like a little ring of vias on these. So I actually did, one of the things I've done kind of while I've had this apart is I pushed some wires through these holes, just for a logic analyzer, and sniffed some of these pins and definitely saw some stuff on some of them when the system turned on. I'm still curious as to how they're storing, you know, basically the configuration memory. It might be more effective of a mechanism to just try and reverse the binary for the micro. You know, get a update image, see if you can figure out how they pack it. You know, and then I'm not sure. I mean, this thing, it's not going to be running Linux, but it might be running like a tiny OS or something along those lines. Wouldn't surprise me if there's some GPL violations in here somewhere. So one of the things you might notice is I'm not tightening any of these screws very hard. So I'm kind of going to put them all in, flip over, let's see, that goes into there. So here's, you can see actually, one interesting thing is if you look at like some of this funky little ground strapping here, I don't really see any way I can take this apart without having to deal with some of that. But there's, you know, this isn't that interesting. It's just got LEDs and encoders. You can actually see that the there's two different types of encoders. There's a plastic shafted encoder. Oh wait, these don't have detents. Yeah, okay, so the metal shafted encoders are the ones with detents and the plastic shafted ones are not. That's interesting. This is also quite a thick board. It's like a 0.093 board rather than a 0.063 board. 0.062. Presumably so that you can push on it, it doesn't flex much. Because it's not extensively supported. And that plugs in there. And then the display. You can see they poke over the edge of the LCD slightly, which is why I had to remove them in the first place. And you can also see that these are flathead screws rather than pan heads, which is strange. I guess it means that the board kind of positions itself more precisely, but on the other hand, not best practice, that. Oh, I see. Yeah, there's some copper springs under there which keep tension for grounding. Because I'm just noticing that the two, so here's the calibration output, and you can see how the ground for the calibration output is just part of this aluminum substrate, or aluminum frame. And what's going on is just, these are not, there's those metal springs on that cover plate that you saw that I removed that are pushing against that, and the end result is there's kind of a big gap here. So as I tighten these, actually I think I will tighten the screws first, because that means it'll be easier to tighten those nuts. But let me just put in a couple of the screws, and then I will test it, and then we will put the rest of it together. We have power LED. That's a promising noise. There's a probe. I see a signal. Looks like something. So, okay, looks like we have a square wave. Alright, square wave. Square wave. Cool, so there you go. Rather exhaustive teardown of one Rigol scope. I'm just going to pop the back off, put the last 3 screws back in, including the ones in under the obnoxious front panel sticker, and there we'll be good to go. So if anyone else is ever in a position where they need to be able to do this, to get the board out, you have to peel the front panel sticker back. And as you can probably see, there are 3 screw holes here. I don't know why, assholes. But so these 3 screw holes here are what actually hold the, you know, they're kind of the remaining aspects of what holds the front panel in place. And you can't get the front panel off, and as a kind of as a rejoinder, you can't get the boards out without, you know, at least somewhat damaging this sticker. And you can kind of see it takes little notches out of them as they get pulled over the pots. Fortunately, I think, yeah, the knobs basically cover the damage it does, but that's still really annoying. So if anyone else is ever in a position where they need to be able to do this, to get the board out, you have to peel the front panel sticker back. And as you can probably see, there are 3 screw holes here. I don't know why, assholes. But so these 3 screw holes here are what actually hold the, you know, they're kind of the remaining aspects of what holds the front panel in place. And you can't get the front panel off, and as a kind of as a rejoinder, you can't get the boards out without, you know, at least somewhat damaging this sticker. And you can kind of see it takes little notches out of them as they get pulled over the pots. Fortunately, I think, yeah, the knobs basically cover the damage it does, but that's still really annoying. So, here's something fairly interesting. This is kind of continuing on the ongoing saga of me attempting to get a meaningful frequency response plot of the Rigol DS4014. So what we have here is an HP 8620C sweep oscillator. So what this does, and this is an HP 86222B RF plugin. So this is a 0.01 to 2.4 gigahertz sweep oscillator, which basically means that, you know, depending on, you can have like an external control or some other mechanism that where it's basically, it can be treated as a VCO, or it has an internal sawtooth generator which is then fed into the VCO to give you a linear frequency sweep, you know, proportional to a voltage. So you can actually see that what we have right now is that it's currently sweeping from 100 megahertz. Oh no, wait, it's currently sweeping straight up to 2.2 gigahertz. So what I can do is, so right now it's sweeping from it's sweeping from 0.1 gigahertz, I believe. So ergo, roughly 10 megahertz. It only goes down to about 13 megahertz, it turns out, to 1 gigahertz approximately. So let me show you a closer look at this. So what we have here is, you can see it's got a number of knobs, and you can see that right now it's an internal trigger. The sweep time is fairly fast. What is my sweep time right now? Let's see. I have to measure. Counter is going to be channel 3. Right now I'm approximately 62 hertz is my sweep time, so you can see that my seconds are down to 0.01. So that works out. And then you can see right now that we have the stop sweep marker is on, which means that the sweep starts at the start sweep marker, I believe, which is, you can see right here. So it sweeps from the start sweep marker to the stop sweep marker in this case, which is right here, which is at 1 gigahertz. So this is a fairly cool piece of equipment. You can see that this is a plug-in, and they actually have options for a 6 to 12 gigahertz module, a 12 to 18 gigahertz module, and a 2 to 18 gigahertz module. So these are all different plugins that plug in here, and then you can see that the scale here, you know, it's got 4 built-in scales, and you just rotate this. Interestingly enough, rotating this does not seem to have any effect on the output, which is interesting, because I've looked in here and there's some little micro switches on here to determine which rotation state it's in. That may be just for like verifying stuff on GPIB, I'm not entirely certain. So, you know, this can do other stuff, like you can put it into a CW mode, where you just put it, you know, you push the CW button, and then basically it just outputs the frequency set by this pin here. And you can have, you know, other stuff, delta F, which is basically I'm actually not sure what's that in. It's in megahertz. So this is basically delta from the set frequency in megahertz. And then you can have there's a CW vernier, which is this. Oh hey, it just started raining. You can't hear it. The fan in this is louder than the Rigol. So the CW vernier is this over here, but this is old, and as you can probably tell, it doesn't actually do anything right now because the grease in here is so ancient and sticky, it's useless. But anyways, the issue I'm having with this piece of equipment is that its output is not flat. So as I sweep it, there's some amplitude modulation, and the issue I'm having is that because, again, the region of interest for the Rigol scope is basically 0.1 to 2 megahertz, 200 megahertz. That 0.1 to 0.2 gigahertz. That we're so far at the end of one of the ranges that there's a fair amount of amplitude modulation, and I can't get a very meaningful. Reading simply because I have to compensate for the amplitude modulation in the output stage to properly measure like the peak-to-peak voltage on the Rigol. So what I have done for that, and I am going to attempt to do now, is, oops, a little bit. So here we have, so you can see I've got two scopes right now. Actually, the way this works is it's coming out of here. Well, you can see that this purple trace is the sweep output. Let's see, oops, I'm no longer triggering. Here we go. So the purple trace is the sweep. So you can actually see it's kind of an asymmetric sawtooth, and by turning the sweep control knob, I can change the, as you can see the pots are rather filthy. I can modify the sweep duration, and it goes down to very low. Right now it's, you know, you can have a 100-second sweep. I mostly don't use that. Let me turn off the CW right here. But what I have here is I've got a 7A19 50 ohm input impedance RF front end in my 7904, and this main frame of this scope is good up to 500 megahertz, and this is actually a 600 megahertz plugin. So what I'm going to attempt to do is do basically, what I'm going to attempt to do is use this scope to trim the output gain vernier. Actually, where is it? Here it is. So I can adjust the output amplitude. So what I'm going to attempt to do is use the amplitude adjustment to trim this so that the various amplitude modulations are flat at the various points at which I take data. I take measurements, and then since I now have a flat known good, I can then get a meaningful plot. So anyways, so what I think I'm going to do is, well, first thing we can do is I want to turn off channel 3, go to auto. Let's see, I need to go. So you can see here we have this is let's see, I gotta turn my 44.8 megahertz. So one thing of interest is that, actually let me show you this before I try to spend a lot of time plotting this stuff. Turn this off temporarily. So you can see right now I have if you can make out that it's 44 megahertz. So if I turn this up, and a lot of this wobbliness is amplitude modulation in here. So you can see right now, so let's see, let's go to delta F. Oh, that's interesting. Does that mean it's wobbling across? I don't know how. Oh, I think so. When I hit delta F, I think it's sweeping between this frequency. Anyways, so there's 50 megahertz. You can see we're up right about 96, 100 megahertz right now. You can see that it's pretty damn flat, straight up to 100 megahertz. But here's where it gets interesting. That's 200 megahertz. And, it's, let me, statistic off. So we can see that right now my VP to P is, let's see, I think my probe is 1x. So we can, let's see, I gotta reset the statistics. So you can see right now that we have an average of 1.48 volts at 200 megahertz. So if I drop down to, say, 80 megahertz, we're up to about 2.16. So it's not a significant drop. It's about a drop of like 24% or so. But where it gets really trippy is, you know, there's a 566 megahertz. And we're down to 700 millivolts, so we're down by about 2/3. But you can see, you know, that's a pretty clear waveform. I mean, I can't zoom in any further because of its limitations, but you can see we're sampling at 4 gigasamples per second. And, you know, I mean, wildly enough, you know, I have to keep turning up the front end gain. Whoops. But, I mean, 796 megahertz. You know, again, we're down to 160 millivolts, so we're down well into the stop band of the filter. But I suspect that it's not like an RC roll-off. I think what they probably have is they simply have a gain roll-off in part of the front end. So as your signal gets higher frequency, you get more gain roll-off. But, I mean, and you can see there's a huge amount of amplitude modulation, which is simply because we're starting to hit the point. I mean, here's 960 megahertz. And you can see it's still triggering fine, there's no issues. There's a waveform. You can see it's not really doing synapse interpolation. But if I go over into dots, you can see that we're pretty obviously getting 4 samples per... Let's see, where is my... I don't want to change the grid brightness. I can't make the dots any brighter, unfortunately. But you can see, you know, that's 4 samples per waveform at 959 megahertz. So everything aside from perhaps the input gain is functional up to many, many times the rated bandwidth of the scope. And there you can see it with the sine wave. And, you know, basically right around here, right around 950, 960 megahertz, the trigger kind of falls apart. It stops triggering. You see, it's no longer triggering. But I actually suspect that if I do a menu force, stop. So right now I'm at roughly 1.1 gigahertz or 1.08 gigahertz. Let me turn on vector. So you can still make out the sine wave, though it's starting to kind of fall apart. I mean, I wouldn't want to use it. You can obviously see the triggering is just not happening. But nevertheless, there's still something that is determinable to be a sine wave, even if it's, you know, 3 sample points per cycle. And then right now, it's basically gone at about 1.4 gigahertz. Anything that resembles a sine wave is just totally gone at about 1.4 gigahertz. And you can see that there's definitely a fair amount of... Let's see. But I mean, now we're down to 600 megahertz, and you can see that that's a noticeable waveform. So one thing I can do to make this a little more visible is I can say, let's sweep. So, actually I gotta turn on this other channel and I gotta trigger off of that. It's kind of, you can see there's some jitter, but there is a sweep from, oops. So that is a sweep from basically 100 megahertz to a gigahertz. Oh, derp. So my trigger levels were just wrong. Also, so it turns out I'm just lame. So there's a little jitter, and that's almost all in the waveform generator. But you can see again, you know, it's probably 500 megahertz right in that point there. And you can also see this interesting gain modulation. You can see the ripples on here, which are a function of the signal generator, because if we look at my tech scope, get it out of trigger. Yeah, there we go. So you can see again, this is flat to a higher frequency, but again, it's very similar. Actually, oops, why did I go out of focus? So if I set my sweep top end to 500 megahertz, so you can actually see it appears there's some roll-off somewhere else. There may be some impedance mismatch issues here. It may just be shitty coax. But again, you can see how actually what is going on, because if that's only going up to 500 megahertz, the scope should be entirely capable of displaying that. So there's kind of an interesting look at some of the amplitude modulations. Let's kick over into CW mode. So you can, basically there's 13 megahertz, and you can see how it wobbles down. Oops. Where's my trigger? There it is. So one thing of note is that this scope more or less stops triggering right at its rated bandwidth. No, I got it going a little better. But if I put it in peak-to-peak mode, you can see that it works up to, well, that's a gigahertz. So I can actually, well, it's not triggering anymore, so I can't do anything meaningful there. There we go. So now we are at, there's 700 megahertz. So let's see, turn the intensity up. So you can start to make out a waveform that's, but the triggering is still barely working. There we go. But you can see, right now I'm 200 megahertz over the top end bandwidth of this scope mainframe. But in any event, you can see that, hey look, 700 megahertz. And on the Rigol scope, so if I get the triggering going right, because we're triggering on the wrong channel, because there's no longer any sweep. Let's see, I want to be edge triggered again. Channel 1, edge. I'm not triggering on the right channel again. Source channel 1. Ah, there we go, I just need. So you can see there's our 700 megahertz waveform. And the only one of the big things that they do for this scope is that you can see that they limit the maximum time step. Right now it's 5 nanoseconds per div. And there's actually a chap on YouTube who says that his scope, apparently ate its non-volatile memory somehow. And now it's convinced it's a 4054. So I'm not sure how this works. They may be toggling an attenuator in or out on the front end somehow. But in any event, you can see that, I can make that out, and you could probably dump this to the computer with one of the Rigol utilities, pick up the stuff on the EEV blog, and get something out of that. But in any event, you can see this whole thing is kind of strange. I've been having so much trouble with the signal generator just because it doesn't really do what it necessarily claims it's going to be doing, which is, it's a sweep generator more than a reference signal generator. Let's see, there we go. So, one of the problems I have is, again, that's a cool picture. That's cool looking. I mean, it's just so not flat over its amplitude range that I don't really know what to do. I've tried to, really what I need is a better signal generator. I haven't really been able to successfully compensate this. I've tried once already and had a lot of other issues. And it's just fiddly. Let's see what I can do. Anyways, let's just wait for a while. So. Yeah, so look at this. Here's me just slowly panning the frequency. You can see some of the output flatness issues I'm having. So I'm only adjusting the frequency, but you can see how much it wobbles. So I'm not going to be able to really get any meaningful benchmarks out of this. It's interesting how it's kind of choppy. I'm not going to get any meaningful benchmarks. I'm kind of actually thinking I'm going to just give up on this whole idea. Just because it's so bad. And the trimming is not working. Anyways, so there's just a quick little demo that, you know, hopefully I'm going to fix some of these RF generators in a little while, and there's a little demo of the RF performance of the Rigol scope, which obviously goes way higher than they spec it does in the manual. Also, if you thought the fan in the Rigol was bad, this motherfucker. That's a fan.